Okay, welcome everyone again to the fourth day of talks in astronomical observational techniques and instrumentation. This is the fourth day, and this is the last talk of the day. It counts to be one of the two best talks we have today. And the speaker is Brittany Vanderhoof, and she'll be talking about AGN at high redshift.
Thank you. Hi, I'm Brittany, and today I'm going to talk to you about a project I worked on where I was identifying active galactic nuclei at high redshift from galaxy spectra, as you can see from my very non-creative title. So my interests lie in the field of galaxy formation and evolution, and I'm sort of on a personal mission to approach this topic from a multi-wavelength approach and sort of build a repertoire of tools that I can use to sort of chip away at the smaller details of this bigger picture. And with that being said, I think we're all pretty familiar with when we start to immerse ourselves into the field of research that we want to get into, that we're reading the literature and the progress that the field has made, and naturally questions can come up that you're kind of like, I wonder what that's all about. So this project was a great opportunity to take one of those questions and actually work through it using the techniques that the current experts in the field use to solve the problem, instead of just reading their diagnostic methods and their results. So that was actually really cool. And with that being said, we'll take a quick look at my outline. At the top, I have my science question: can we identify active galactic nuclei from galaxy spectra at high redshift? Again, my title was not creative, I took it from my question. So what I'm going to do is we're going to talk about what an AGN is, why is it important, how it connects to my big picture, and then we're going to spend some time talking about data analysis and techniques, how we can kind of chip away at this, and then finally we'll get to my results and talk about that and hopefully be able to answer this question. So I want to first start by identifying this term I keep using, but active galactic nuclei is a supermassive black hole at the center of a galaxy that is actively accreting material, so material is falling in that black hole. And it's known that all massive galaxies have supermassive black holes at their center, and there is even further evidence that the galaxy and the black hole kind of evolved together. The details aren't very well known, so this is something that we're kind of trying to work on. And so getting into that, one of these types of galaxies that are interesting for galaxy evolution at high redshift are called LIRGs, and from their name, these are galaxies that are very luminous in the infrared. So they're very luminous in the infrared, and this is because they have really high star formation, but there also could be contribution from an AGN. And it turns out that a high fraction of these galaxies actually do have AGN, so it becomes apparent that AGN can play a role in galaxy evolution when you look at this type of situation. And this is sort of what motivated me to use this as a topic for my presentation. So let's talk about AGN a little bit. I think most of us have seen the standard model for an AGN, so I'll kind of go through it quickly. But at the center, we have our black hole. Just around that, we have our accretion disk, which is where the material is that's falling in. Just outside of that, we have our obscuring torus, and over here we see that we have our broad line region, our narrow line region, and then finally we also have our jets. And this picture is the same model, but instead what we're looking at here is the emission signatures that we see from the different components of our AGN. And I'm just going to point out the ones that I focused on my presentation, which is most of my data is looking at the narrow line region, which emits invisible, but I also did consider some X-ray signatures, which would be coming directly from the accretion disk, and finally I did look at a little bit of IR data, which would be coming, in the AGN model, would be coming from our torus. Overall, what you kind of want to get from this picture is the idea that by looking at a multi-wavelength, taking a multi-wavelength approach to this, we can necessarily examine specific components of our AGN. And so like I mentioned before, AGN play a role in galaxy evolution, and one of these ways that they can do that is, for example, during this process of accretion, in this active state, the black hole has a really large effect on the galaxy around it, because the process of accretion causes these large emission winds and these jets, which necessarily can push material out of the galaxy, and that can in turn inhibit star formation, and this quenching of star formation is going to play a really big role on the evolution of that galaxy. So one way to better understand the relationship of the black hole and galaxy evolution is to naturally just increase our amount of AGN that we have identified, so that we can study the growth of a black hole and also study the characteristics and growth of the host galaxy and see what correlation comes out of that. Now, of course, identifying AGN isn't always straightforward. AGN aren't out there just saying, hey, look at me, I'm an AGN. It's a little bit more difficult than that. And so, for example, like the LERGs I mentioned earlier, which are really bright due to star formation or to AGN, that's an example where we really need to be able to separate the two to be able to better study that evolution, or the effects that both of them have on the evolution of the galaxy. Okay, so here is an example of spectra from some galaxies, and what I want to point out here is just the emission of some lines that are going to be key for sort of trying to go through and separate the star formation in AGN, and these lines are H alpha, H beta, and then O3 and N2, and you'll note here that the O3 and the N2 have brackets around them because those are forbidden lines. And like I said, one diagnostic tool, which is the one that I used in my work, takes advantage of these lines to separate star formation and AGN, and this is called a BPT diagram, named after its creators, Baldwin, Phillips, and Turlevich, who produced this in 1981, and it's still used very well. But this really plots the relative flux of the ratio of certain emission lines to separate our AGN and our star forming regions, or the contribution from star formation versus the contribution from AGN. And so what you see here is that we have plotted in the x-axis, we have our N2 to our H alpha, and the y-axis we have O3 to H beta, and what is plotted here is 100,000 galaxies, and just note that H2 is a proxy for star formation, so think of that as star formation. And what you see happens here when you plot your galaxies is that you have a nice region of a sequence of star-forming galaxies that trace metallicity from low metallicity to high metallicity, and our AGN move up onto this part of the diagram. Now, this happens because the highest energy of photons that you can get from star formation alone is limited by what the most massive stars can produce. Whereas in an AGN can produce much harder ionizing photons, which will necessarily increase the amount of flux of the forbidden lines compared to your hydrogen recombination lines, and that necessarily means that our AGN are going to fall to the top on the right, whereas our star formation is going to be a little bit lower and to the left. And so that's what you see on these diagrams. And the thing to note next is that Cooley et al. In 2006 came up with a theoretical upper limit for photoionization models. So this is sort of a threshold for the amount of flux that you can see in these lines that comes from the energy that is given from star formation by itself. So this is the most you can see if there's only star formation. And then here in blue is an empirical line that was developed after that by Kaufman et al., which is just a tighter fit to our data, and that gives us a little bit of an area in here which is defined as the composite region, and it's a little trickier to separate than just the other two regions because you can have many different things going on in here. These could be star formation contributions, there could be AGN contribution, there could be a little bit of both, and that's something that's still being figured out and worked on. But I'd like to note that for this plot at the local universe, which is plotted for, this looks really nice. You can see a really nice trend of the separation of your star formation and your AGN, and it looks really great. Now, at higher redshift, it's not quite as simple, as we'll see when we get to that. We'll talk about it a little later, but for now, this works. And so, like I said, this is gonna bring us into my data and my analysis. And like I said, I wanted to look at stuff a little higher redshift. And traditionally, spectral classification of galaxies at high redshift has been difficult because our lines are now shifted from the optical into the near infrared. And historically, conducting these large scale surveys, so hundreds of thousands of objects, on ground-based telescopes in these wavelengths has been really difficult. And thankfully, more recently, we've had the multi-object spectrographs, which makes this task of targeting large amounts of galaxies at a time in this redshift a lot easier, which is great. And the Subaru telescope is one of such telescopes. I flew to the island this weekend to take this picture for you guys. And so on Subaru, we have FMOS, which is a fiber multi-object spectrograph. And this is just a nice picture of the telescope. Here's some people for scale. It's a pretty huge telescope. You got your mirror right there. And then over here you see your spectrographs and another person here for reference of how big those are, which are pretty big. And I guess for short people like me, what this is saying is that objects may be bigger than they appear on the diagram. So, moving on, FMOS. So there's 400 fibers, which is a ton. It's a huge field of view. There's 30 arc minutes. And on a perfect night, the perfect layout of galaxies, what this means is that necessarily you can look at over 100 galaxies, target over 100 galaxies at a time, which is great. Also because the fibers are controlled by actuators, so they'll actually throw everything into position for you really well, and so that's great. So this is the problem we needed to sort of fix, trying to look at more objects at a time. All right, so let's talk about my data, guys. So the Cosmos survey is a huge collaboration. It's a multi-wavelength survey, and what they did was they actually used FMOS for some of their near-infrared data, which is the data that I use. So I use part of their survey, and over here on the left, we have the Cosmos field as compared to the moon. And it's a 2 square degree area on the sky. And then on the right here, this image is showing you the circles are FMOS pointings, so it's showing you how they use FMOS to sample the Cosmos field. So that's how we did. And like I said, they have much more data than just this data. In the main survey, I actually used their X-ray coverage as well, which covers the whole area, and their IR coverage, but we'll talk about that later. So I got my data from the Cosmos survey, and this data was collected over the past couple of years by the team, and they resolved it sort of along the way, and they were also able to actually measure the flux of the lines that I was interested in. So that was already done, and they did this by simple applying a Gaussian to the emission feature and determining what the flux count was for each of those lines. So here I am. this huge FITS file, thousands of objects. I need to extract my data. And what I wanted to do was target objects where all 4 of the lines that I'm interested in for the BPT diagram had a signal to noise greater than 3. So, IDL, we all know from our homework, it's difficult because we're all still learning it. So this took me a while, and I kind of struggled with it for a while to get it to target those objects, pull out the flux, pull out the error, give me the numbers I need, compute my ratios, plot them so that I can actually see what relation that I get. I struggled for a while, and then all of a sudden, one night it just sort of clicked and it started working. I got a little overexcited, and I'm like, holy crap, Brittany, this is working. So I got really excited. I threw in some plot commands because I really wanted to see where my points landed, because, I mean, that's the coolest part of the project, right? Seeing what happens. So really excited. Here comes the data. Wrong. All right, Brittany, you had one job, and that was to make a publishable plot. This isn't it. Clearly all I did was plot the path that my cat takes at 3 o'clock in the morning at the speed of light, because this is not a BPT diagram at all. So I had to like take a step back, go back, realize that I need other things on here. So figured out error bars. I labeled my axes. I was feeling like an overachiever, so I put a legend in. But we'll get there in a second. Promise it'll be better than this. And first, I want to take you back to this BPT diagram quickly, because I promised you that it wasn't quite the same at higher redshifts. And like I said before, 100,000 galaxies on this plot, so much easier to see a trend. And also this was for the local universe, whereas my galaxies are at a redshift about 1.5. So here's a plot that shows the QLE line that we were looking at before. This blue one is the same one for a redshift of 0, but there is a natural shift in this line as you move up in redshift, and this is due to the difference in ISM conditions. So the conditions of the gas are different at a redshift of 0 than they are at a redshift of 1.5, 3, any of those. So you have to take that into consideration with your model. And here we're just obviously going to pay attention to the, I think it's green, right? Yeah, the green line and the blue line, which was our 0 line, the one we saw before, and the one that will more easily correlate with my data, and that's what I actually plotted on my plot. So here we are, the right stuff, finally. So right off the bat, you can see, well, right off the bat for me anyways, because this is what I cared about, right? Right off the bat, you can see that there are definitely some of my objects that fall into the AGN region. Okay. Yay. But let's talk about this a little bit more. So here are my QLE lines. So this is my 1.5, and this is my 0 line. And if you want, there's no evidence that these galaxies would be AGN, which is what it would say if we left it at the redshift of 0 line, right? So it sort of corresponds with the shift. My data sort of corresponds with the shift in our QLE line, because, like I said, there's no evidence that these necessarily all, there may be some composites in here, but they don't necessarily all have AGN. And so that's one thing to know about the line portion of that. And then we do have, all of our star-forming galaxies and maybe a small composite region that we can look at later, because like I said, that's more of a tricky area. But again, this is great. We found some AGN, A+. But I wanted to go back and into the Cosmos survey, because like I said, they had some other data. And what I pulled out was a different data set, which had millions of objects, including mine, and any X-ray detection that there was. And at this redshift, X-ray detection means definitely AGN. And so I just wanted to see how that would fit in with my BPT style of figuring it out, see how that fit in with my data. So went back to the drawing board, more code, pulled that out, overplotted it, and what we see here is that I had 3 of my objects, which I think I didn't mention earlier, but after I used my selection of having a signal to noise greater than 3, I ended up with 73 objects. So not not quite 100,000, but. So anyway, so 3 of those actually had some X-ray detection, which is great, and it's even more awesome, I guess we can use as a word, that they fell on ones that were in my AGN region, and that sort of means that, hey, maybe I did this right, and also it just means that this process is still a really cool process to look at. But anyways, finally, getting back to my original interest with the luminous infrared galaxies, I also wanted to take a look at which one of these galaxies had far infrared data. And I did the same process before. I went to the table, pulled out which one of my galaxies had infrared data, and I plotted it here. And this is, like I said, an interesting thing for me in the future. It's not super necessary for what I was trying to accomplish here, but it helps us to look at which one of these objects show detections in the far infrared as well, and we can see that there are some that definitely have AGN, and then there's a couple in our star-forming region, but then possibly if we imagine where our composite region falls, there are some in that region as well, so that's stuff that in the future is possible to continue to look at. But getting back to the point of this, my question here was, can we identify active galactic nuclei from galaxy spectra? The short answer is yes. We can with confidence say that a handful of my objects do have AGN in them. However, some of my other objects will take a little bit more looking at and figuring out what's going on to determine if they did or did not have them in there. That's it. Thank you.
Questions?
So, not that this was related to your question, but I was just curious that it seemed like at the redshift of 3, there were a lot fewer AGN in that half the region because you're pushing the bar up farther the higher redshift you go. Is that kind of what people expect to see from, like, that there would be fewer AGNs in the earlier universe, that kind of idea?
I don't know if that necessarily means that there would be fewer AGN, but what it does mean is that the star forming contribution is shifted up further, so they can have higher energies, which means that their flux ratios will be higher. So that's really, I think, a better meaning for this shift here.
Okay.
Go ahead.
For the standard model of an AGN,
Oh boy.
the picture on there had abbreviations that I all understood. The next slide.
Oh, this one?
Except for RF. What is RF? Coming out of the chip.
I mean, I'm just gonna say that I think it's radio, but
Oh, okay.
so I'm pretty sure we can identify some of the stuff in radio, right? Quasars, radio.
Well, it looks like
We learned something about this once.
the wavelengths are long, right?
Oh, I see.
But I'm not sure if that is.
I mean, it's coming from the jet, so that's probably just frequency.
Yeah, radio frequency, yeah.
Okay.
Other questions?
I had one. So you said that H2 is a proxy for star forming?
Yeah,
Can you explain why? Maybe you did.
I mean, that's what the author used to say star formation. I think she felt that was more, I don't know what the word is,
Why, I'm
more
sure
appropriate way
I'm sure
to
there's a reason. I guess I don't
say it, because I guess H2 regions, singly ionized hydrogen has to be star formation to ionize it. I'm not sure, but she specifically chose to use H2 to
Okay.
mean star formation.
Okay.
I have some questions. If you could go to slide 5. What's that ionizing cone?
So I'm gonna take a stab at it, okay? I don't know for sure. I'm gonna say that that is the region which can easily be ionized by the AGN, because, I mean, out here, out here can't be because it's obscured from the energy coming from there is being obscured by the dusty torus, so these areas are gonna be the areas that
So I guess it must mean that something is doing the ionizing,
Mhm.
and something's being ionized.
Oh, yes, correct.
So what is the thing doing the ionizing? Where does the ionizing radiation come from?
So maybe I didn't say this in the beginning and thought that I did. So the ionizing radiation, that is coming from the AGN itself, the process. So the accretion disk, the movement of.
Okay, so that's producing the ionizing flux?
Correct.
And then what's getting ionized?
So maybe I didn't say this before. When I said broad region and the narrow line region, those are actually clouds of gas. And those can see some of this radiation here. This UV can come up there and ionize those clouds of gas. So, yeah.
So what I think is confusing to me is that in this picture,
Mhm.
it leads me to believe that the ionizing cones are the black regions.
Oh, yeah,
Oh, yeah.
maybe. I see what you mean.
And I would have thought that the ionizing cones were the purple regions.
They are.
It's just a question of labeling.
Mhm.
I can now see that they're trying to point to
Yeah.
the purple regions.
Yeah.
Okay.
I
So
stole this from these guys, by the way.
sure. So go to slide 6.
Yeah, sure.
What's a forbidden line?
All right. So I knew someone was going to ask this question. So forbidden line, like many things in physics, is a very poor term for what that means. What I think that where that came from originally is that we couldn't create those lines in the lab, right? But that doesn't mean they don't happen. And I guess I think it has something to do with how long the particle needs to be able to emit a photon. Something along those lines, and out in the galactic realm, it has enough time to do that.
I think it's related to the density that you can achieve.
Mm-hmm.
And
Yeah.
if it's too dense, it'll collisionally de-excite,
Yeah.
or something like that. You won't get a radiative de-excitation,
Yeah.
so you won't get the lines.
Yeah.
But it is a phenomenological definition, which is annoying.
Yes.
Go to 7.
Sure.
Okay.
Oh boy.
Speaking of phenomenological and
Look at everything.
AGN research, which I purposely don't do. So let's see here. Why does this look like a V? What are those dots? You have these black dots that sort of,
So the black dots are all galaxies.
but they're data points,
Yep.
they're observations.
They're all data points.
So what makes them awesome. So why are they distributed in a V?
Okay, so when you plot these specific lines, these people here found that what happens is your star forming contribution. So the relative ratio of this forbidden line to this recombination line and this to this makes galaxies that have high star formation fall in this galaxy sequence, is what they call
Yeah, but
it.
you're just telling me phenomenological words for you're just saying that when you plot points with these axes, it makes that shape.
Yeah.
Okay, from physics, why does this look like this?
I guess because maybe
If you don't know, that's okay.
maybe this isn't the answer you're looking for, but I thought, okay, so the amount of energy that can be produced from a star formation affects the amount of flux seen in these lines. And for star formation, it falls in this region because it's limited by how much the highest energy photons that can be created from star formation. And that falls in this region.
So given your knowledge of what H alpha and H beta is, and what those forbidden lines are, why does it curve that way? Is it the case that, I'm talking about the star formation branch, right? Because that's, I think that's what you were just talking
Yep,
about. It's the left side of the V.
Yep.
Right. So it looks to me that in the upper part of that branch,
Mm-hmm.
there is less nitrogen 2
Yeah.
as compared to H alpha.
Mm-hmm.
It's like either the H alpha is getting bigger or the nitrogen two is getting smaller, or it could be both,
Okay,
going from the bottom to the top of the curve, right?
yep,
And then on the y-axis, it looks like O3 is getting stronger versus H beta as you go up towards the top of the branch, right?
mm-hmm.
Is that more star formation or less star formation? Or is that not relevant?
I think that more star formation is over here,
It's on the bottom.
right?
I don't know, I'm asking.
Yeah, because the metallicity kind of falls this way. So, to me, higher metallicity means more star formation.
Where's metallicity?
That's just from my research, sorry. It's not actually on here, but the metallicity follows low metallicity to high metallicity from this paper, the literature. I think it just has to do because N2 is a better indicator for metallicity. So they use the increase in N2 to mean that that's
So
high
this
metallicity.
might be, the answer to this might be complex.
Okay.
I don't know, like I said, I purposely don't do this. This is
Mhm.
one of the reasons why I don't. But you could talk to your advisor about this, but I've always felt that a good AGN researcher knows the physics of what's happening, not just the pictures of a graph.
Mhm.
And most of the research has to do with pictures of graphs.
Mhm.
But then there are some people who actually know what's happening, like
Mhm.
the physics behind it.
Mhm.
And those people, I think, have the best ability to do research, right? Because then you can explore things based on predictions about what hypotheses you might have about the physics,
Mhm.
as opposed to just the pictures. I would ask the same thing about the AGN. Like, why would AGN be in a different place based on physics? And I presume some people have done stuff like this, right? They've modeled AGN emissions, and they've modeled star formation emissions, and maybe they've attempted to reproduce this plot just based on theory, not actual measurements.
Mhm.
But I don't know what the answer is to that. Do you know the answer to that? Like, why the AGN?
Why the agent are up here?
They tilt over that way, yeah.
They tilt up here because of the harder ionizing photons.
So the
The energy.
harder ionizing photons, let's think about that. That sounds like that makes sense, right? Because the AGM model shows some gamma rays or UV, and maybe that's extraordinary beyond what a star formation region would produce,
It is.
right?
Yeah.
And that part of the diagram maps into more nitrogen 2
Yeah.
as a function of H alpha and more O3 as opposed to H beta. So
Mhm.
it sounds like the Balmer lines, I don't know which is diminishing and which is increasing, or if it's both, but,
I think
but
it's-
as a ratio, the Balmer lines are getting weaker compared to the forbidden lines.
Correct. And it's an increase in flux of our forbidden lines compared to our recombination, hydrogen
And
recombination.
why is that related to a harder ionizing fuel?
I guess it has to do with the energy need. I did read about this, but I'm not really good with the words, but it has to do with the type of energy that's needed to bump those levels up. I'd have to go back to my reading,
Yeah.
which I don't have with me, I'm sorry.
Yeah, no, so I
Yeah.
think it's good to know.
Mm-hmm, yeah.
It's the kind of thing that I think, you should know soon if you're gonna be an AGN researcher, and then know forever,
Mhm.
like, because this is a basic plot.
Mhm.
These lines here that you've overdrawn, I'm not sure I'm right about this, but are they kind of an average of all the points that we're looking at?
This line is theoretical. This line is empirical, so possibly for that one.
But what is it? I don't know what it is.
This is just a theoretical line that was developed based off of the nature, like the actual physics, so like the nature of what happens when these molecules are ionized and what would be seen from star formation alone. This is a theoretical
Oh, that
upper
was-
limit
Those are
to-
just the star formation part.
Correct. This is a theoretical upper limit to the ionizing, the photoionization models from star formation.
Okay.
That's what it's for.
And why do they look to be a little bit shifted to the right with respect to the particular black dots in this plot?
so this one was theoretical, and then when they went back in and made an empirical tighter fit, but still, you know, staying with, so they used this was Kaufman et al., and this is Cooley. She had the theoretical upper limit, and then he came back in, I'm sorry, it's also a she. Kaufman came back in and made a tighter fit correlation, so that's an empirical one, and that's just because in this region here, it's sort of is it just star formation? Is there star formation and HDN? So it's a little bit of a different story this close to the line.
So maybe Hewlett had a data set and then made that black dashed line based upon a data set?
This line here,
Yeah.
this was a different person, but possibly.
Oh.
This person did use data. This
Okay.
one, this empirical one was done after we saw how it fit data,
Okay.
yes.
So let me, okay, I think that's it. Any more questions that you thought of as we were talking about this stuff? Okay, thanks very much.